Sweet, set, and ready to go. So in any event, welcome back. So after our small little walkabout into the world of Markov chains, we're actually ready to jump into some pretty cool randomized algorithms, or so-called Monte Carlo algorithms. So hooray for randomization. So the big idea here is that we're actually going to be building up some really small, efficient algorithms that may or may not always work. Then the big idea is then going to be to run that small, simple little task over and over and over and over again until we hopefully get the scenario that does in fact work. So to give us kind of a fun example that plays off of our current theme, we're actually going to be looking into the world of taking a nice little graph or a network and then trying to slice it into two components. So this question is often referred to as a question looking into a cut, and in particular, the minimum cut of a particular graph. So down below, I have this nice little picture. I have my little dude over here with his little samurai sword, and I have a very interesting network of all of 6 nodes with what, 1, 2, 3, 4, 5, 6, 7 total edges. And this person is totally eyeing up this little edge right here, because if they chop that edge in half or remove it, then you can see that my network blows up and then it's no longer connected. So that's the theme for the day, is that we're going to be looking at these cool little randomized algorithms, or these Monte Carlo algorithms, and we're going to be branding them in this kind of window of trying to identify minimum cuts. So to look at kind of a slightly more interesting example, we're going to introduce some notation here, and then we're actually going to set the stage for what I'm going to identify as the simple algorithm. So officially, the min cut question is presented in front, is that you're going to give me a graph. This can represent whatever you want it to be. So it's going to be some collection of nodes or vertices, as well as these little transitions or edges between them. And I want to go about trying to identify some specific edges that I could delete or blow up, if you view these as kind of bridges or something like that, in such a way that's actually going to take this graph and split it into 2 components. So down below, I have a slightly more sophisticated graph, and that has all of 7 total vertices with 10 edges. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can see that this thing is actually going to be a multi-graph, because I'm going to have a double edge between E and F. So you can think about F as being some little city. They tried to safeguard it from attacks in that I don't just have one channel going into it, but I'm going to have 2. And right off the bat, you can actually see that if I were to make those 2 little cuts right there, obviously I would rip this thing into 2 components, in that F is no longer part of our network. So that's one potential cut. You can see that I could also maybe cut those 2 things right there. So if I slice the line between B and C, as well as slice the line between G and E, that I've actually ripped this thing into 2 components as well. At this point in time, you can also see that if I were to just make a single cut anywhere, you would actually not rip this thing into 2 pieces. Maybe you just severed that line between B and C. So there's no longer a direct connection between those 2 things, but we have enough redundancies built into this that I could actually flow down to G, over to E, and then up to C. So in general here, we have to make at least 2 cuts in order to actually rip this thing in half. So you could also rip off the A maybe, and what color haven't I used? Let's use this mac and cheese color. Cool. And that's actually basically it for the number of ways that I could make 2 nice little snips and actually rip our graph into 2 components. If you want them slightly fancier written out, I have them down below. So I have cut 1, which would actually be to isolate A. I have cut 2, which would be to isolate D. I have cut 3, so the green one, which is then how to isolate F. And then kind of the bigger cut here is then going to be sever those 2 little middle lines. So the B to C and then G to E. So if you snip those 2 things, then we properly are going to rip this graph into 2 components as well. So a couple really interesting things obviously are going to emerge at this point in time. So hopefully you've got some wheels churning in your brain right now, which is going to say, okay, if I gave you some random graph and I told you to try to identify a cut, and then try to think about trying to do that as optimally as possible, one idea that might spring to mind would be to, okay, go through all of your little vertices and identify the one that has the smallest degree. If you sever all of the lines around that, that actually does give you a cut, and it may or may not be optimal. It's actually part of the reason why I introduced this extra little edge down here, because if I only had a single line going into F, F is connected to this network, but it's not very well connected. So if I made that single cut, then F would actually be removed from it. So I added an extra little bit to actually make the degree of F then up to 2, try to safeguard it a little bit. So if you look at this thing, there's a couple different vertices that all have degree 2. So A has degree 2, D has degree 2, and so does F. And we can actually see that all of those little singletons can be removed by actually severing all of the lines into them. So we can actually break them off with just the degree. And that's true about any singleton vertex. You can always remove it from the graph just by cutting all of the lines that go into it. It may or may not be the most efficient way to split the graph into 2 components, but it does technically always work. So the goal here is to try to think about how to do this as optimally as possible. Maybe I don't care about kind of isolating a single node. I just want to make sure that the whole system at least has ways to get around things. So if I view this as a really big electrical network or something like that, I want to make sure that everything actually has some amount of flow. I don't want to rip this thing into 2 bins. So the question of trying to just isolate singleton vertices is going to give us a cut, and it may or may not be the best one. If you actually go back to that initial little kind of cheesy example that I have here, this is actually a nice little counterexample that would show that if you were to just isolate the single kind of lowest degree vertices and then isolate them, that's actually always going to take 2 cuts. So these things out on the outside all have degree 2. So to isolate any one of those, you'd have to make 2 little cuts. However, I can actually rip this graph into 2 pieces by just making 1 cut. So if you were to think about that middle thing as being some bridge over a nice little river or something, we're back to our river crossing problems all over again. You can see that these things that lead into it are somehow kind of like the major cities that are going to be connected by this little bridge. And then they're going to be fairly connected to the rest of the network, but there's only one little path between them. So if you blow up that bridge, then I'm ripping this thing into 2 components, and we do have a nice little cut. And this scenario would be a cut size of 1. So it hopefully should be sounding off some alarms of, I can't just look at the degree of singleton vertices. There's something more actually happening here, which is actually what makes this particular question really interesting, is that there's a local property, but also some type of global property happening at the same time. Is that if you were to have just a singleton kind of doing its own little thing off there, it's really easy to cut that thing off. But you could also have 2 really, really well-connected graphs that are separated by a couple tiny little bridges that are also really easy to remove. But the way that you would go identifying those scenarios are going to be a little bit different. And that's where this kind of randomization process is going to come into play very nicely, is that we want to design a technique that can handle both types of graphs, as well as everything in between those. What we're going to do here is we're going to actually introduce this nice little simple algorithm. It's going to make use of this kind of nice little sucking in of vertices aspects. So we're going to randomly select edges, and we're going to kind of zip them all back together until we're down to a nice little stopping point. It's going to be pretty cool and tidy. So we're going to execute this little contraction, this little zipping over and over and over again. And then we're going to end up with something that we can actually read off of fairly easily. So I'm going to pause the video there so we can start up a proper little example. I'll run through a couple of examples by hand, and then we're going to kind of bring about this kind of Markov, or not Markov, but this Monte Carlo. Too busy saying Markov from the last section. We're going to bring about this Monte Carlo aspect to try to showcase how we can actually boost our success and actually get into something that should hopefully hum fairly nicely. So stay tuned. We'll be right back.